Hello, we were discussing about Newton's second law for a single particle till now. We have looked at the kinetics of a single particle, we have looked at a particle with varying mass or with mass flow, and in this lecture we are going to start with the discussion of kinetics of a system of particles. When we have a number of particles in a system, then how does the equation of motion look like? In this lecture, therefore, we will generalize Newton's second law of motion for a single particle to a system of particles and look at the work energy relations. Consider a system of n particles as I have shown you in this figure. The position vector of the ith particle is indicated by r I vector in certain inertial coordinate system, and similarly the jth particle is indicated by r j vector. These particles might be interacting amongst each other, and F I j is the force that acts on the ith particle due to the presence of the jth particle. They may or may not be connected, but they are interacting, they have some form of interaction, and this force of interaction we are indicating by F I j when we are looking at the ith particle and considering the force due to the jth particle. Then we say F I j, and F j I similarly is the force on the jth particle due to the presence of ith particle. These forces, because of Newton's third law, are equal and opposite. They are called internal forces between particles I and j. There is no self force, that means the particle ith particle does not apply any force on itself. Therefore, F I that vector must be 0. In this way, all particles are possibly interacting. We then consider external forces indicated by capital F. On the ith particle it is capital F I vector, on the jth particle capital F j vector, and so on. Now, for the individual particles we are going to write down the Newton's second law. For the first particle, for example, we can write mass of the first particle times acceleration of the first particle is equal to the external force on the first particle plus summation of all these internal forces because of the other n minus 1 particles. From particle 2 to particle n, these are applying forces F 1 2 to F 1 n. F 1 1 of course is 0. And like this, when we write Newton's second law for all the particles, for the nth particle we have mass of the nth particle, acceleration of the nth particle must be equal to force on the external force on the nth particle plus summation of the internal forces because of the other n minus 1 particles. These particles are from 1 to n minus 1. If I sum up these equations, then let us see what happens. On the left hand side, I have summation of m I r I double dot summed over I from 1 to n, and on the right hand side I have summation of all the external forces and double summation of all the internal forces. Now, because of Newton's third law, as I have noted here, F I j must be equal to minus F j I. Now, this double summation has everything, it has F I j, F 1 2, F 2 1, F 1 3, F 3 1, etc., and it gets summed over. Therefore, this summation obviously must vanish. What is left with what is left now is this form: total mass times acceleration of center of mass must be equal to the total external force applied. Here there is one step that needs to be pointed out. I have used this definition of center of mass. Summation of mi r I must be equal to the total mass times position vector of center of mass. This is the standard definition of center of mass. This has been used. Therefore, here I can take time derivatives, I can take one time derivative, I can take two time derivatives. Therefore, summation of mi r I double dot, which appears here, must be equal to total mass times acceleration of the center of mass. And on the right hand side we have the summation of all the external forces. So, it is the total force acting on the system. The double summation of the internal forces, as I just now mentioned, must vanish. This is an extension of Newton's second law for a system of particles. Newton's second law for a particle says that mass times for a particle of constant mass says mass times acceleration of the particle is equals to the net force acting on the particle. When you have a system of particles, Newton's second law, this generalized Newton's second law, tells us that mass, total mass of the system times acceleration of the center of mass must be equal to the summation of all the forces acting on the system. Now, this is slightly different from the normal Newton's second law, because it tells us only about the acceleration of the center of mass. Individual particles are not, I mean, you have to then write down the individual Newton's second law for each particle and solve. But for the system, we have total mass of the system times acceleration of center of mass must be equal to the net force acting on the whole system. Let us consider a problem. This problem is from the book of Merriam and Craig. The three small spheres treated as point masses are connected by cords and a spring and placed on a smooth horizontal surface. If a force F equal to 6.4 Newton is applied to one of the cords as shown, find the acceleration a g of the center of mass of the spheres for the instant depicted. So, we have three spheres connected in a certain fashion, and a force is acting on a cord which connects these particles, and there is a spring. So, different kinds of connectivities are there between the particles, and the force is somehow transmitted to the system through that cord. Now, for this system we can write the equation of motion for the center of mass, not for individual particles. We will not be writing for the individual particles, but this generalized Newton's second law for the system of particles is applicable. And you see, as we have discussed, it does not depend on how the particles are interacting amongst themselves. The internal forces all disappear in the final generalized equation of motion, and that is for the center of mass. Therefore, the equation of motion for the center of mass, total mass of the system times acceleration of the center of mass must be equal to total force acting on the system. In this case, there is a single force F of which is 6.4 I cap Newton in the coordinate system that I have shown here, and the total mass of the system, if you add up, is 1.6 kilogram times acceleration of center of mass is 6.4 I cap Newton. Therefore, our acceleration vector, acceleration of center of mass, is 4 I cap meter per second square. This problem shows that it does not depend on the interconnection of the masses, as we have also shown, seen in the derivation of the generalized Newton's second law for a system of particles. The interconnections or interactions do not matter when we sum over all the particles of the system. Some of them may not be interacting also. For example, if one particle is free, another might be moving, then the center of mass, the equation of motion of the center of mass is governed by the generalized Newton's second law for the system. Next, we will look at the work energy relation, work energy form of this generalized Newton's second law. For the ith particles, let us say for the first particle, I can write this Newton's second law for the ith particle. Mass of the first particle times acceleration of the first particle is force acting on the first particle, external force, plus summation of all the internal force because of the other n minus 1 particles from 2 to n. Like this, I can write for all the n particles, Newton's second law for the all the n particles. Then I dot product the first equation of motion with r 1 dot, second equation of motion with r 2 dot, and the nth equation of motion, nth particle, equation of motion of the nth particle, I dot it with the velocity of the nth particle. And then I sum over of all the particles. What do I have? On the left hand side, this we have seen before as well. On the left hand side, we have summation of mi ri double dot dot ri dot, and this we have seen before that this can be written as summation of d dt of half mi ri dot dot ri dot, and that is precisely what I have written on the left hand side. And you can recognize what is there in the within the brackets. It is the total kinetic energy of the system. Okay, we will proceed first with the right hand side. On the right hand side, I have summation of fi ri dot, fi dot ri dot. That means the dot product of the force acting on the ith particle with the velocity of the ith particle and summed over all particles. And I have a double summation of the internal forces Fij dot velocity of the ith particle minus velocity of the jth particle. Now, this summation, double summation, is over I and j. The double summation is over I and j. The bracketed expression, as I just mentioned, is the total kinetic energy of the system, because it is the sum of kinetic energies of individual particles. So, it is the kinetic energy of the system, total kinetic energy of the system. And therefore, the rate of change of total kinetic energy of the system is given by summation of force dot velocity summed over all particles plus double summation of the internal forces dot product with r I cap, which is the velocity of the ith particle minus velocity of the jth particle. So, this is our relation, what we have obtained from the previous steps. Suppose there is no interaction between the particles, these are free particles moving freely, they are not interacting, there is no force of interaction. Therefore, Fij are all 0. In that case, the second double summation on the double summation on the right hand side, which is the second term on the right hand side, that drops off, and what we are left with, I can integrate over time. On the left hand side of that expression is time derivative of the kinetic energy. Therefore, when I multiply by dt and integrate over the system moving from state A to state B, then I have on the left hand side it is the change of kinetic energy dt integral from A to state B is the change in kinetic energy as the system moves from A to B. On the right hand side, it is Fi dot dRi, which is the work done on the ith particle, and now this is summed over as the system moves from state A to state B. Therefore, this is the sum of work done on the particles summed over all the particles. Therefore, this can be written in a simpler form as the change in kinetic energy is equal to the total work done by all the forces acting on the system as the system moves from state A to state B. This is the work energy relation. This form of work energy relation we have seen for a single particle, now we are seeing for a system of particles. And this relation tells us that the change of kinetic energy of the system as it moves from state A to state B is equal to the work done by all the external forces on the system. If the work done by all external forces is 0, then kinetic energy is conserved. So, kinetic energy in state B, the final state, is equal to the kinetic energy in state A, which is the initial state. We look at a second situation in which we consider a rigid frame, which means that these particles are kind of connected. So, this is one particle and they are all connected or interconnected by a rigid light frame. So, this frame is light, but it is rigid, and there are a number of particles which are connected by this rigid light frame. Or it could be inextensible connections, like we have discussed problems of blocks connected by inextensible strings. So, for all such situations we can consider the second case. So, what does the second case tell us? When it is a rigid frame, what happens in a rigid frame is Ri dot minus Rj dot. This is the relative velocity between I and j. Ri dot, so is the velocity of ith particle minus velocity of the jth particle. That becomes equal to omega cross Ri minus Rj. Now, this we have discussed in kinematics. The relative velocity between these two mass points is omega cross Ri minus Rj, the vector connecting these two mass points, but this is true only when these particles are rigidly connected, right. It is like these two particles are on the two ends of a rigid connection, or it is connected rigidly. So, this whole rigid connection has a single omega, and Ri dot minus Rj dot is omega cross the relative vector Ri minus Rj, and this was discussed extensively under kinematics. Therefore, if this is true because of rigid connectivity or rigid frame connecting the particles, then what we conclude is Ri dot minus Rj dot, which is now this expression omega cross Ri minus Rj. Therefore, this relative velocity must be perpendicular to both omega and the relative vector Ri minus Rj. What is important here is it is perpendicular to Ri minus Rj, which is the relative vector, which I have shown here. Ri minus Rj is a vector going from here to from the jth particle to the ith particle. So, this dashed vector is Ri minus Rj, and because Ri dot minus Rj dot is perpendicular to Ri minus Rj, therefore, the dot product of this term with Fij, remember Fij is also along this direction. Fij is also in the direction of the line joining the two particles. and r I dot minus r j dot is also is perpendicular to this line. R I minus r j is this, and omega cross r I minus r j is perpendicular to this line. F I j is along the line, therefore, this dot product must also vanish, because F I j is perpendicular to r I dot minus r j dot, the relative velocity vector. In that case, again the second term on the right hand side of our work energy relation drops off, and we are left with the change in kinetic energy on the left hand side and the work done by external forces on the right hand side, and we get back the work energy relation as before. But only thing you have to remember, this is the change in kinetic energy of the total system on the left hand side, and that is equal to the work done on the total system by all the external forces. Now, we have considered these two situations where the second term on the right hand side drops off, either there is no interaction or if the particles are connected by a rigid frame. In that case, the second term drops off, but where is the second term relevant? This question naturally arises. This second term is important or relevant for flexible bodies, because for flexible bodies it is not guaranteed that the relative velocity is orthogonal to the internal force vector direction. Okay, so there can be storage of energy. So, the special cases that we have discussed till now, the second term on the right hand side had dropped off. Now, we are going to look at a general decomposition of the force, externally applied force. As we have seen before, that this force, externally applied force, can be decomposed into conservative forces and non-conservative forces. This F I superscript c represents conservative forces and F j superscript n represents non-conservative forces. Now, different particles might be under conservative or non-conservative forces, that is why I have indicated by two indices I and j. The conservative force part, F I conservative dot d r I, as we have discussed this before, is minus d V I, the potential of that particular force on the ith particle. So, the potential field that the particle is in. Therefore, I can write summation of all these d V I's as V, the total potential of the system, because individual particles are in different potential fields in general, are in different potential fields, they can be in general in different potential fields. Sum of all these potential fields is V, and this term on the right hand side minus d V I can take to the left hand side and combine with the kinetic term. Therefore, d t plus V integrated from state A to state B, and you know that t plus V, kinetic plus potential energy expressions, this summation is known as the total mechanical energy of the system, and that must be equal to whatever is left on the right hand side. It was the work done by the non-conservative forces. So, F j non-conservative dot d r j, and summed over all particles on which this non-conservative forces are acting. This is our final expression. Therefore, the change in energy d E integrated from A to B is equal to summation of the work done by the non-conservative forces as the system moves from state A to state B. After performing the integral, I have the change in the total mechanical energy of the system is equal to the work done by all non-conservative forces as the system moves from state A to state B. If there are no non-conservative forces or these non-conservative forces do no work, then the total mechanical energy of the system is conserved. Now, this we have discussed under this special situation that the internal forces do not contribute. Therefore, for non-interacting system of particles or rigidly connected particles, we have the conservation of kinetic energy or the total mechanical energy, as the case may be, as we had discussed. In case that second term is present, we will have energy storage or rejection from the system, because this internal forces, they are going to store or they are going to release energy. Now, let us look at the decomposition of the kinetic energy. This is our general work energy relation, and the kinetic energy of the whole system is within that bracket. The bracketed term is the total kinetic energy of the system. We can write R I, this is the vector R I, in terms of the position vector of the center of mass and this relative vector rho I. If I do that, I can also derivate it, time derivate it, and substitute in the expression of the kinetic energy, as I have done here in this step. Now, I open this dot product, I open the brackets and simplify. What I obtain after simplification, and this is a straightforward algebraic step which you can very easily do. Only thing you will have to remember that we are using this expression, this identity, that summation of m I rho I is 0, and this follows from the definition of center of mass. How does it follow? You know that summation of m I r I, position vector of the ith particle. So, this sum must be equal to summation of m I times r g vector. This is from the definition of center of mass. This is how we define center of mass. Therefore, I can take whatever is there on the right hand side to the left hand side and write it as summation of m I r I minus r g is equal to 0, and r I minus r g, as you can see from here or from the figure, r I minus r g is nothing but rho I. This is nothing but rho I. Therefore, it follows that summation of m I rho I vector is equal to a 0 vector. This condition when you use here, and because this summation of m I rho I is 0, therefore, summation of m I rho I dot, this is also 0. So, when you use all these conditions, you come to the second step from the first step. Now, let us look at these individual terms and what they mean. This is the expression we have obtained for the kinetic energy. The first term can be written as half total mass of the system times velocity of the center of mass square. Here you will notice that this only has that index I, therefore, this summation over I sums, it is a sum of all the individual mass values, is the total mass of the system, half total mass of the system times velocity of the center of mass squared. This is velocity of center of mass vector, and dot product with itself, it gives the magnitude square, plus summation of half m I rho I dot dot rho I dot. The first term is the kinetic energy because of the motion of center of mass. Kinetic energy because of the motion of center of mass, and the second term is the kinetic energy due to the relative motion of the particles about the center of mass. Therefore, the total kinetic energy of the system is composed of two parts: the kinetic energy of motion of the center of mass with all the mass concentrated at the center of mass. So, it is the kinetic energy of all the mass concentrated at the center of mass and its motion, the kinetic energy because of its motion of the center of mass, plus the kinetic energy of all particles moving about the center of mass. This velocity rho I dot is the relative velocity that you should note. Rho I dot is the relative velocity of a particle with respect to the center of mass. What happens for a rigid frame? For a rigid frame, as we have discussed in kinematics, rho I dot, if everything is connected rigidly, so all particles are kind of rigidly placed with respect to the center of mass. Therefore, this rho I dot, rho I vector dot, the time derivative of rho I vector is equal to omega cross rho I, because this vector within the rigid frame is not changing, the vector rho I within that rigid frame is not changing. Therefore, this del del t of rho I is 0, as we have discussed in kinematics, because now G, the center of mass, and the particle, ith particle, both are points of the same rigid frame. Therefore, rho I dot is only omega cross rho I. We are going to use this expression a little later. Let us look at an example. Three identical small spheres which are to be treated as particles, each of mass m, are fixed by three identical light rigid rods as shown. The assembly moves on a smooth circular track in the vertical plane. If the unit starts from rest at theta equal to 0, theta is indicated in the figure, with a force of constant magnitude P, always acting perpendicularly at the midpoint of the rod as shown, determine A, the minimum force P min which will bring the unit to rest at theta equal to 60 degree, and B, the common velocities V of spheres 1 and 2 when theta is equal to 60 degree if P is 2 times that P min value we calculate in the part A. This problem is from the book of Merriam and Craig. This is a system with a rigid frame. We are going to use our work energy relation, and for that we need to fix a datum for the potential energy, because this whole system is in the vertical plane. Therefore, we have acceleration due to gravity as shown acting vertically downwards. We have gravitational potential energy, and the datum I fix at this level as shown. This level is this level coincides with the level of the center of mass of this particle when theta equal to 0. So, when theta equal to 0, this center of mass of this particle is at the datum position. This is just a choice, you can choose datum anywhere else. We use the work energy relation. The total change of total mechanical energy from state A to state B is equal to the work done by all the non-conservative forces. Now, this applied force P does not have an equivalent potential, therefore, we consider that to be a non-conservative force, and we have to calculate the work done because of that non-conservative force. Now, on the left hand side we have the total mechanical energy at B minus total mechanical energy at A. Now, total mechanical energy at B, state B, which is obtained when theta equal to 60 degree, the total mechanical energy at that location is kinetic plus potential. Now, it must just reach that position with theta equal to 60 degree. Therefore, at that position the kinetic energy at B must be 0, it is only potential energy. Similarly, the system started off in state A at theta equal to 0, it started off with 0 velocity. So, the kinetic energy in state A is 0, it is only the potential energy in state A, and this change in the total energy, which is essentially the change in potential energy of the system in states B and A, is equal to the work done by the applied force, and the work done by applied force you can easily calculate, it is P times ds. This ds I write as r by 2 d theta. So, r by 2 d theta is ds. Okay. Now, we are going to write down the expressions one by one. The potential energy in state B, there are two mass points. This mass point remains fixed in state B as well as state A. Therefore, I do not consider that, because in a difference that will get removed. It is only the potential energy because of these two particles. For this particle 1, it is mgr 1 minus cosine pi by 3. When it reaches, when theta equals to 60 degree, this looks something like this. It reaches this configuration. Well, this is 60 degree, and from the start this is 120 degree. The potential energy of the individual mass particles you can write down. For the lower mass particle, it is 1 mgr 1 minus cosine of pi by 3. For the upper mass particle 2, it is mgr 1 minus cosine of 2 pi by 3. 2 pi by 3 is 120 degree, because the second particle reaches this level. And in state A, the lower mass point, the potential energy becomes 0 essentially, cos 0 is 1. So, this expression becomes 0. The second term gives us minus mgr 1 minus cos of pi by 3, and this must be equal to the work done by the external applied force, which turns out to be pi by 6 PR, and from here you can get P min as 9 mg by pi. In the second part of this problem, we have to find out the velocity, common velocity of this of the two particles 1 and 2 when 2 times this P min is applied. In place of P min, we are applying 2 times P min. Then again writing down the work energy relation. Now, we note that at the final state the system will have some velocity, because now we are applying 2 times P min, it will have some velocity. Therefore, there will be kinetic energy contribution in state B when theta equal to 60 degree. And I have written out the expressions of the kinetic energy for the two particles, as you can see here. This is for the individual particle, and for two particles it is 2 times the kinetic energy of the individual particle, they are identical particles. And we have the as usual the potential energy expressions, and potential energy in state A. So, total energy in state B minus total energy in state A must be equal to the work done by now 2 times P min, which turns out to be 3 mgr. And from here I can straight away calculate the velocity of common velocity of both particles 1 and 2, turns out to be under root 3 by 2 g r. This is straightforward algebraic step which you can complete. So, to summarize, we have discussed the generalized Newton's second law for a system of particles, derived the work energy relation, looked at some special cases of work energy relation and some application to some numerical problems. With that, I will close this lecture.